On November 18, 2013, NASA's Mars Atmosphere and Volatile Evolution, or MAVEN spacecraft, was launched toward Mars with the goal of scientific examination of Mars' atmosphere. It is hoped that science experiments conducted by MAVEN will offer scientists answers to questions about what happened to Mars' atmosphere and water. Around 3.5 billion years ago, Mars had a magnetosphere and an atmosphere which was thick enough and warm enough to sustain liquid water. Today, the atmosphere is all but gone, as is the water. What was Mars' atmosphere like 3.5 billion years ago? How can scientists examining today's atmosphere on Mars know what the atmosphere, magnetic field, and water were like on a planet so many billions of years ago? Instead of concentrating on the surface, all of the spacecraft's instruments will concentrate on Mars' atmosphere in an effort to answer these questions. MAVEN carries a total of 8 scientific instruments in 3 packages: the Particles and Fields package, the Remote Sensing package, and the Neutral Gas and Ion Mass Spectrometer. There is no camera on MAVEN. MAVEN will study the boundary between the planet's current atmosphere and outer space. MAVEN measures what's coming into Mars' atmosphere, what the current atmosphere looks like, and finally, what's escaping from Mars' atmosphere. The spacecraft flies in an elliptical orbit from 150 kilometers to over 6,000 kilometers above the surface. It will make 5 deep dips down where the atmosphere is 30 times denser. This allows the spacecraft to sample several altitudes of the atmosphere. MAVEN is a box 7.5 feet square by 5 feet high. The high-gain antenna is 6.5 feet in diameter. Solar panel wings span 37.5 feet wide. The solar wings are bent at an angle of 20 degrees because as MAVEN travels through the upper atmosphere, the air pressure will increase to a point that could disrupt flight dynamics if the panels were flat. 2 instruments on MAVEN measure the current composition and structure of Mars' atmosphere. They are the Imaging and Ultraviolet Spectrograph and the Neutral Gas Ion Spectrometer. The Imaging and Ultraviolet Spectrograph, IUVS, instrument measures the characteristics of the upper atmosphere and ionosphere from a broad global view and is located on a movable platform arm extending down from the body of the spacecraft. It is positioned here so that it can point in any direction, regardless of where the spacecraft itself is pointing. This also gives the instrument its full global view of the planet. The purpose of the IUVS is to make 3-dimensional models of the upper atmosphere's major molecules, atoms, ions, and their isotopes. The spectrograph is an instrument that can tell us what gases are present in the atmosphere by spreading an object's light apart, revealing signatures of molecules so that we can tell what they are. For example, the light wavelengths of hydrogen and deuterium, or heavy hydrogen, require a high resolution to separate them into wavelength lines for analysis in the spectrograph. And the IUVS is capable of doing this. Scientists can look so closely that they can tell the difference between hydrogen and deuterium. The lighter hydrogen is assumed to have escaped into space, leaving behind the heavier deuterium. Here's how it works. Run electricity through a tube of gas and it glows. If you run this through a prism, you get the full spectrum of colors. Run it through an instrument like the IUVS, and what you see is a full spectrum of specific wavelengths of light, causing them to appear as different colors to the instrument. Run electricity through a tube of hydrogen gas, and it glows pink. That is the fingerprint of hydrogen gas. Every gas has its own unique fingerprint. So wherever we look, we can tell how much carbon dioxide, how much oxygen, and how much hydrogen or argon there is. And that is how the IUVS can tell us from a broad global view what the current atmosphere of Mars is made of. Located on the movable platform below the spacecraft, along with the IUVS, is the Neutral Gas and Ion Mass Spectrometer, NGEMS. It is located here to keep it away from its own gases and allowing it to face different directions. Like IUVS, NGEMS determines the composition of the upper atmosphere. But rather than from a global view like IUVS, NGEMS takes a closer, more detailed view. NGEMS is the only instrument on board that allows us to analyze the atmosphere immediately around the spacecraft, called in situ. Since IUVS measures the atmosphere with a broad global view and NGEMS takes a closer, more detailed local view, the two instruments will complement each other. NGEMS studies how neutral gases and ions in the Martian atmosphere interact with the solar wind. The red cap on the left is a protective cap covering an ionization source found on the NGEMS instrument. It is fired off to remove it when the spacecraft is in position around Mars. NGEM uses this electron gun to bombard the gas molecules into smaller charged particles or ions. Concentrating on the more detailed view, NGEMS is interested in how much space is between atoms and molecules in the atmosphere and how that space changes with altitude. As the spacecraft skims through the upper layer of the atmosphere, it can sniff out atom by atom, molecule by molecule, to figure out what the composition of the atmosphere is. The very top of the atmosphere is called the exosphere, where the atmosphere is so thin that even atoms don't bump into each other. NGEMS measures the profiles of a number of different chemicals, including argon. Measurements involving argon will be particularly interesting. Unlike other chemicals in the atmosphere, argon doesn't react with its surroundings, so argon is likely to be the most simple, straightforward indicator of atmospheric loss today. Since lighter isotopes escape the planet more readily than heavier isotopes, atmospheric loss will appear as a change in the number of heavy argon isotopes compared to the number of light argon isotopes as altitude increases. Here's how it works. This is an illustration of an electron beam ionizing a neutral gas, which is what NGEMS will be doing. The gas first enters the spectrometer, hitting a piece called the ion source. Here, a stream of electrons hits the molecules, breaks them into fragments, and giving each fragment a charge, creates an ion from a neutral gas. That ion then gets focused into an analyzer called a quadrupole filter. It is called quadrupole because of its 4 rods. Different electrical voltages are applied to the 4 different rods. Each specific voltage isolates ions based on each gas's specific mass. As the ions spiral down the rods, they get separated out, so only the fragments we want to see make it all the way through. Everything else flies off in a different direction. They then hit a detector, which counts not only what kinds of ions come through it, but also the number of ions of a particular mass that come through it. What you have then is a mass spectrum, creating a picture of all the different gas particles present in the Martian atmosphere. And that's how NGEMS gives us a detailed measurement of the composition of the upper atmosphere. The suprathermal and thermal ion composition, or static instrument, is mounted on the articulating platform along with IUVS and NGEMS. While IUVS and NGEMS are studying what is already in the atmosphere, static concentrates on what's going out of the atmosphere. Since MAVEN will be examining Mars' atmosphere during a period of relatively high solar activity, static's information will show how variations in this solar activity relates to differences in atmospheric loss. Thermal and suprathermal ions mostly come from the solar wind, the usual suspect causing the atmosphere to be swept away. The common theory is that because Mars lost its magnetosphere, the solar wind swept away its atmosphere. Another thought, however, is that other properties such as excess kinetic energy carried by the solar wind can transfer enough of this energy to atmospheric particles that they can attain escape velocity regardless of the magnetic field status. Our Sun constantly emits high-energy photons. When one of these photons enters the atmosphere of a planet, it can crash into a molecule, knocking loose an electron and turning it into an ion. Ions by themselves don't do much, but when a magnetic field is nearby, the ion will spin around the field. Our Sun generates a gigantic magnetic field carried by the solar wind. As the sun's magnetic field sweeps past the planet, some ions will be carried away. Other ions, depending on where they form, won't get carried away, but will hit the top of the atmosphere. These ions can then crash into other molecules and fling atoms everywhere. Some of these atoms can be knocked or sputtered into space, causing atmospheric loss. Static captures these high-speed ions, sends them through an analyzer, and measures their velocities and characteristics. Located on a dedicated boom mounted in between the two LPW booms is the Solar Wind Electron Analyzer, SWEA. SWEA measures electron properties of the incoming solar wind. SWEA can tell the difference between electrons found in the solar wind and those in the Martian ionosphere by identifying their different energies. By identifying where solar wind plasma ends and planetary plasma begins, SWEA will be able to zero in on where the very top of the planet's ionosphere is located. Scientists are trying to understand this boundary layer between the solar wind and the planet's ionosphere because this is the region where planetary material is being lost. It will also help scientists learn how these particles already in the atmosphere get enough energy needed to boost them high enough into the atmosphere so they can escape. The solar wind is packed with charged particles and magnetic field lines that can interact with particles in Mars' upper atmosphere. The ions must travel along magnetic lines in order to leave the atmosphere. On MAVEN, the SWEA and MAG instruments work together to map out the crustal magnetic fields and determine if these fields are open or closed due to changes in the sun's magnetic field and rotation of the planet. An open magnetic field line allows particles to escape, and a closed magnetic field line will turn the particle back to the planet. SWEA measures these electrons flowing along the magnetic line to find out if it is open or closed. Electrons enter SWEA through two deflectors which are open to space. These electrons are sorted and analyzed according to their energies, telling scientists which electrons are coming from the solar wind and which electrons are coming from the planet's atmosphere. Positioned on the tips of either end of MAVEN's solar panel wings are MAVEN's magnetometers, MAG. They weigh less than 1 pound each. Since magnetic fields can emanate from other components of the spacecraft, the magnetometers were placed as far away from the other instruments as possible. These are extremely sensitive sensors that can detect a magnetic field that is 1,000,000 times weaker than the Earth's magnetic field. The solar panels also contain wiring which is laid out in a special pattern that cancels out any stray magnetic fields. The magnetometer measures the strength as well as the direction of magnetic fields. Unlike Earth's global magnetic field, which surrounds the entire planet, Mars only has patches of magnetic field left in its crust. This has created pockets of atmosphere that are protected against solar wind. The magnetometer helps us see where these crustal or mini-magnetospheres are located. These mini-magnetospheres influence how the Martian atmosphere interacts with the solar wind. Here's how they work. A fluxgate magnetometer works essentially like a compass, but instead of a spinning needle, electromagnets are used to generate magnetic fields. If you wrap a coil of wire around a bar of ferromagnetic metal and run a current through it, the bar becomes magnetized and generates its own magnetic field. Reverse the current, and the field reverses direction. If you do this over and over again, the two directions cancel each other out. However, when an external magnetic field is present, like those on Mars, the two directions are thrown out of balance, allowing you to measure the external field. By combining multiple fluxgate sensors, you can measure a magnetic field in 3 dimensions. The magnetometers help us see where the atmosphere is protected by magnetospheres and where it is open to the solar wind. The job of MAG is to measure interplanetary, ionospheric, and solar wind magnetic fields. The Langmuir Probe and Waves Instrument LPW consists of 2 parts. The first part is a pair of 2 cylindrical sensors that are installed away from the spacecraft at the tips of 2 7-meter-long booms. This allows the sensors to measure electrons without being influenced by the spacecraft itself. The LPW instrument is designed to study what is coming into Mars' atmosphere. The pair of booms and sensors generate a variable voltage to the booms, which excite Langmuir waves in plasma, measuring electron energy and density in the local area around the spacecraft. This will help to more clearly define the density and boundary of the ionosphere. The second part of the LPW instrument, and sometimes referred to as the ninth instrument, is the Extreme Ultraviolet Sensor, which is mounted directly onto the body of the spacecraft, facing the Sun. Extreme ultraviolet radiation is high-energy ultraviolet radiation generated naturally by our Sun's corona and brought to Mars by the solar wind. LPW also works together with MAVEN's magnetometers, giving scientists a picture of the extreme ultraviolet radiation coming out of the Sun and flowing into the ionosphere. This energy can also heat up ions, which can also cause escape. The job of LPW is to help scientists understand the science of what is coming into Mars' atmosphere, how the solar wind and ionosphere are structured, and how they interact with each other. The Solar Energetic Particle Instrument, SEP, consists of two identical instrument boxes fixed mounted at 90-degree angles from each other and on opposite sides of the body of the spacecraft. SEP detects the highest energy ions coming into Mars' atmosphere. By measuring the impact of the solar wind on Mars' upper atmosphere, the instrument is designed to study the energies of hydrogen and helium ions emitted by our Sun during solar storms, solar flares, and coronal mass ejections. SEP will also help scientists understand what effect these particles have in ionizing the upper atmosphere, as well as their role in the sputtering process. The job of SEP is to determine the impact that solar energetic particles from solar flares, solar storms, and coronal mass ejections have on the Martian atmosphere. Mounted on one corner of the spacecraft's body and oriented toward the Sun to ensure good coverage of the solar wind is the Solar Wind Ion Analyzer, SWIA. SWIA is a single sensor which measures the solar wind and magnetosheath ions, including their density, temperature, and speed, in order to determine the energy input into the upper atmosphere. It takes these measurements in the undisturbed interplanetary medium at the point that they encounter the Martian environment. It measures the speed of the solar wind as it passes by the planet. SWIA measures solar wind ions, which are very, very fast protons and ionized hydrogen coming out of the Sun. SWIA measures the speed of the solar wind when it comes in contact with Mars' upper atmosphere. These measurements will provide data on the total solar wind input to Mars and how the solar wind and upper atmosphere react with each other. SWIA and SEP both explore the solar wind. SEP concentrates on studying the very highest energies of hydrogen and helium ions emitted during solar storms, solar flares, and coronal mass ejections. SWIA concentrates on measuring the speed of the solar wind as it passes by the planet. Although not one of the science instruments aboard MAVEN, the Electra Communications Relay plays a key role in the exploration of Mars. It will serve as a backup communications system for the Curiosity and Opportunity rovers currently exploring Mars' surface. Since there are currently 3 orbiters circling Mars and providing relay communication, MAVEN's Electra won't be used immediately. However, as these orbiters reach the end of their expected life, or the need arises, Electra will step in to communicate with and relay data back to scientists on Earth. MAVEN, meanwhile, will communicate with Earth using its high-gain antenna. These signals will be received using NASA's Deep Space Network. The antenna is fixed on the spacecraft, so the whole MAVEN spacecraft has to be moved to point the antenna at Earth for its regular communication sessions that are expected to be about 5 hours in duration, twice a week. NASA's MAVEN spacecraft will be studying the atmosphere of the red planet in amazing new detail, providing scientists with a comprehensive, in-depth look at the Martian atmosphere. Using all of the science provided by MAVEN will allow scientists to form models of Mars' atmosphere as it was 3.5 billion years ago, and answer questions about how Mars lost its atmosphere, allowing the planet to dry out. These models may also allow scientists to answer questions like whether the atmosphere was once substantial enough and warm enough to sustain liquid water on the surface and possibly support life.